Let's talk about rotations, reflections, and translations. We're also going to talk about some symmetries. A transformation moves a figure through a plane. One kind of transformation is called an isometry. It's also called a congruent transformation. Translations, reflections, rotations, and glide reflections are all examples of isometries. Dilations are also transformations. They're called similarity transformations. That means we're stretching or shrinking the shape. So in this case, the size of the shape can change. We're not going to talk about dilations right now. We're going to concentrate on the isometries. So let's start with the translation. A translation is also sometimes called a slide. And when we translate a figure, what we do is we move it any direction in the plane. Maybe we move it left, or we move it diagonally, or we move it up. But whatever direction we move it, we notice that the size of the shape doesn't change, and its general orientation doesn't change either. In a reflection, which is also sometimes called a flip, our shape will be reflected across a line of symmetry, which acts kind of like a mirror. So if we reflect this R across this vertical line of symmetry, we have its reflection, its flipped image. That line of symmetry can be in any direction at all, so we can reflect across a line of symmetry that has any relation to the original shape. It might be in any direction, it might be any distance from that original shape. With a rotation, which is also called a turn, our shape is going to be rotated or turned around some point. So we have to know what the center of the rotation is. In this case, it's this red dot. When we rotate a shape, we need to know what direction we're rotating it. So in this case, the R rotated clockwise, and we need to know how many degrees we rotated the shape. So the R rotated 360 degrees clockwise. Or we might rotate it 360 degrees counterclockwise. Or in this case, we're rotating it 90 degrees clockwise. The center of rotation also does not have to touch the shape. So in this case, the center of rotation is above the R, and if we rotate it 360 degrees clockwise, we would have something that would look like this. Now there is a kind of transformation that combines two of these transformations, and that's called a glide reflection, which combines both a slide and a flip in either order. So we could, let's say, start with this letter R and flip it across this line. So we're reflecting it across the line, and then slide it, translate it down. And we have completed a glide reflection on the original shape. Now we can also perform these transformations on a coordinate plane. For example, let's say we wanted to translate the point -2, 1, 4 units right and 2 units up. So the point -2, 1 would be slid 4 units to the right and 2 units up, and we would have the translated point at 2, 3. We could take the point -2, 1 and reflect it across a line of symmetry. In this case, we're trying to reflect the point -2, 1 across the line x equals 1. Since the point is 3 units to the left of that line of symmetry, we're just going to reflect it 3 units to the right of the line of symmetry, and the reflected point is at 4, 1. And we can perform rotations on a coordinate plane as well. So what if we want to rotate the point negative 2, 1 90 degrees clockwise around the origin? So the center of rotation is at the origin, and we're going to rotate around the origin, which means we're going to rotate the point somewhere along this circle. Now, since we're rotating clockwise and rotating 90 degrees clockwise, we need to find that 90-degree angle from the point to the center of that rotation back to the circle. So we're going to rotate the point 90 degrees along that circle, which would put our point, our rotated point, at 1, 2. So let's talk about a couple of symmetries that are related to these different types of isometries we've talked about. First of all, there's something called dihedral symmetry. So the word dihedral is really telling the story of what's going on here. Di means 2 and hedral means sides. So if we're trying to find the dihedral symmetry of a shape, what we're looking for is a line that we could use as a mirror for the shape, or think of it as a fold line. So could we fold this heart along a line so that we have two sides, dihedral, two sides of the heart matching? And in this case, we do have a line of symmetry that we could fold the heart on, and the two sides would match. So we have one line of symmetry, and in this case we would say that this heart has first order dihedral symmetry because it has one line of symmetry. How about this shape? How many lines of symmetry do you think it has? What is the order of dihedral symmetry for this shape? Well, certainly we have a line of symmetry here. We could fold the shape along this line and the two sides would match. And we have another line of symmetry here, so that's 2, and another here, and another here. So is that it? Is that all the lines of symmetry? There's actually a few more. There's a line of symmetry here, and here, and here, and here. So there's 8 lines of symmetry, 8 lines that we could fold this shape on and the two sides would match. So this shape has 8th order dihedral symmetry. The other kind of symmetry we're going to talk about is called rotational symmetry. Now this is a shape we just looked at, and if we're looking for the order of rotational symmetry for this shape, what we have to imagine is that we're finding the center point of this shape and we're rotating the shape around the center. And what we want to know is, as we rotate, how many times will the shape match up with itself? So here's how we're going to look at this. I'm just going to lay an outline of the shape on top of it, and I've colored one of those triangles on the top so we can keep track of how many times we've rotated it. So I'm going to rotate this clockwise and we'll count how many times it's matching up with itself. So there's 1, 2, 3, 4, 5, 6, 7, 8, and we're back to the beginning. So this shape has 8th order rotational symmetry. So you may think, well, this had 8th order dihedral symmetry, so it must automatically have 8th order rotational symmetry. That's not always true. Think about this shape. This shape has 3rd order rotational symmetry, but it has no dihedral symmetry. There are no lines of symmetry that we could fold this shape on and have the shape match each other on both, or match itself on both sides. So we'll get a chance to practice some of this in class.